Okay, so welcome everybody to the joint colloquium. If you didn't read carefully our email, we are having a music fest after this, so you are more than welcome to go to Grad House with us. I'm about to tell you a very true story about Nick, so listen carefully. It says, back in time, more precisely on high school time, Nick met a beautiful girl with the sunshine in her eyes. That girl inspired Nick to compose a song. Nick took 9 months, listen to that, 9 months, to create that 25 minutes masterpiece, and when he was ready, Nick gave it to her, declaring his love. Nick said, I would like to fill the position of being your boyfriend. That girl answered, sorry, but the position has been taken. With Nick, with his heart in his hands, went to the University of Calgary to do undergrad in PMATH and promised to himself that he will never lose again. By the time he graduated, he was the student with the highest GPA of the Faculty of Science. And he won, listen this, he won not 1, not 2, not 3, but 5 academic medals, 5 academic achievement medals, including the prestigious Governor General's Silver Medal. Nick came to the University of Waterloo for his master's and now his PhD under supervision of David McKinnon. And he met the beautiful area of Diophantine geometry with the sunshine in its protective varieties that made Nick to compose again, to compose theorems that sometimes take more than 9 months. Nick split his heart in 2 pieces, one for math, one for music. The music that makes him play clarinet at the Orchestra di Waterloo. And today, Nick decided to come to our joint colloquium to declare one more time his love for math. So, welcome.
Thank you. All right, so I want to thank Diana and Julian for inviting me to give this talk because I've been wanting to revive this area for a long time. This was work I did as an undergrad, about 2 years in the area of graph theory. So those of you who are more graph theoretically inclined, there's going to be some open problems that I'm going to pose for you, and they're very, very accessible because, as I should know, because I came in as a second-year undergrad, understood the subject, wrote a paper, added to this body of knowledge, but no one seems to touch this thing because there seems to be a history of those of us who do this problem either change areas or leave academia altogether. So don't let this dissuade you. I'm pretty sure this is not a pattern. It's just a really, really fun subject. So again, those of you in graph theory, you're going to enjoy the open problems. Those of you who have never seen a lot of graph theory before, hopefully by the end you should be able to understand some of the terms a graph theorist says to you when you have a conversation with them. And in the meantime, we're going to look at some pretty pictures of graphs. Okay, so this is a graph. This graph is called the Peterson Graph, but that's not terribly important. What is important is that there are 2 parts to this, and if you're explaining this to a 12-year-old, you would call them dots and lines, and if you're explaining them to a group of mathematicians, you would call them vertices and edges. But the dots, well, you just declare yourself as some set of vertices, some set of dots, and you're going to join some of these things up with lines or edges. And some pairs of vertices have an edge between them, some of them don't. Fine. So you can draw them in all kinds of fancy ways, but these are the 2 important ingredients, the vertices and the edges. And this graph is connected for reasons that may seem intuitive. Idea being that I can take any 2 vertices in this thing, I can start following a sequence of edges, and I can get from one vertex to the other. So that's going to be a term that we're going to be using a number of times. By contrast, this graph is not connected for obvious reasons. Okay, so those are the dots and the lines. But my talk is called Dots, Lines, and Arrows, so there's got to be some arrows somewhere. And these arrows are going to be visual representations of graph homomorphisms. Homomorphisms exist between graphs just as they do between lots of different mathematical structures, and they're just going to preserve some underlying structure that we find important. With the graphs, there's not really much to preserve except edges between vertices. So if you've got a graph G and a graph H, a homomorphism between them is just going to be a mapping from the vertices of G to the vertices of H that preserves all the edges. So if I've got two vertices that are adjacent to start with, which I might call V and W, if I hit them with this map, their images are still adjacent on the target graph H. So the definition's all fine and good, but maybe a picture is more helpful. So these blue arrows are representing the mapping that we get on vertices. So this is a map from the graph on the left to the graph on the right. And you can go through edge by edge and check that whenever I've got two vertices that are adjacent, they're going to get mapped to vertices on the right-hand graph that are joined by an edge. So this illustrates some interesting behaviors we can get with these graph homomorphisms in general. They don't really care what happens to non-adjacent vertices. All I care is if they're joined by an edge, then I send them back to vertices that are still joined by an edge. But if they're not joined by an edge, I can send them to the same vertex, I can send them to vertices that aren't adjacent, whatever I like. The game is free to play. So sometimes we want to rule out these pathologies. And to do so, we add some restrictions. So this leads to monomorphisms and isomorphisms. A monomorphism is just an injective homomorphism. So no longer is it possible to map two different vertices to the same vertex. But that's it. An isomorphism goes a little further. So like any notion of isomorphism, it would just be a homomorphism that has an inverse. So if I compose it in either order, I should get the identity map back. But another way of saying this, if you go through the steps, you can see that an isomorphism is exactly a bijection between the vertices of my first graph and the vertices of my second, that not only preserve edges, but also preserve non-edges. So another way of saying that is that if I have two vertices are adjacent on the starting graph G, if and only if their images are adjacent on H. All right, so more pictures. Here is what a monomorphism might look like from this graph on the left to the graph on the right. The graph on the left, by the way, goes by a special name known as a four-cycle, which is probably familiar to those of you who are graph theorists. For the obvious reason. I've got four vertices, and they're adjacent to each other in a cyclic pattern. So I can number them off, 1, 2, 3, 4, in such a way that 1 is adjacent to 2, 2 to 3, 3 to 4, and 4 to 1. So I can do this for any number of vertices. If I do this with n vertices, we get an n cycle. This is going to be another family of graphs that's going to come up time and time again. So and the graph on the right is known as a complete graph for the reason that all the vertices are adjacent to each other. Anytime I have a pair of vertices, there's an edge there. So we've got a graph, or a monomorphism from the four cycle on the left to this complete graph on the right. And again, you can check edge for edge that it's going to preserve all these edges, but no longer can I collapse vertices. I can't map distinct ones to the same vertex. All right, here's an isomorphism, which also coincidentally looks somewhat like some schematic of an atom. But anyway, we have, this is a rotation map from the 6 cycle back to itself. So I've just rotated each vertex clockwise, and certainly there's an inverse map, namely the counterclockwise rotation that will undo this thing, so it's an isomorphism. So you never get vertex collapsing with an isomorphism, and again, non-adjacency is preserved. So these are the ground rules, which you could easily sit down with any 12-year-old in your life and explain. This is just the rules you play with these arrows on this collection of dots and lines. But the game we want to play is more interesting. So this would be a game I would play with myself and an opponent, say. So we're going to agree in advance on some finite graph on which to play this game. And my opponent, she is asked to give me some subgraph of this graph we've agreed on, and a homomorphism from a subgraph of it to another subgraph. This gets passed to me, and my job is to extend this map to a map that's defined on every vertex of my graph. So the question is, can I always win this game? No matter what choice my opponent makes, am I always able to take a partial homomorphism from some subgraph to some other subgraph and extend it to a homomorphism defined on all the vertices? If we're playing on a winning graph, then we'll call that graph an HH graph. These pairs of H's are referring to the fact that my opponent chose a homomorphism and my extension has to be a homomorphism. So we've got these three types of maps in play homomorphisms, monomorphisms, and isomorphisms, and you can mix it up by asking either my opponent or myself to choose our maps from that particular special class. So this particular example I've given here, the 3-cycle, so my opponent could be handing me this particular partial homomorphism, just this one vertex, this other vertex. And in that particular case, I can certainly extend it just to some rotation of this 3-cycle. You can go through all the possible maps and argue that in fact this thing is an HH graph, but I'm going to do something a little more general later, so we'll save the goods for what's to come. So like I said, with there being 3 choices of maps for my opponent and 3 types of maps for me, this leaves 9 types of graph we can talk about for which I can always win this game. So if you've got every monomorphism that my opponent gives me from a subgraph to a subgraph, if I can always extend that to a homomorphism, then we'll call it an MH graph, and you can do this with IH or HI or MM, lots of different letter pairs. And the cool thing about this stuff is that it organizes itself into a nice hierarchy under containment. So graphs that are lower, or types of graphs that are lower on the hierarchy are contained in the ones that are higher up. So every HI graph is going to be both MI and HM, and so on, all the way up to the top where you have IH. So there's an easy way of arguing this, and it basically just depends on the observation that every isomorphism is a monomorphism, and every monomorphism is a homomorphism. So we'll do one test case here, that every HI graph is MI. So suppose we've agreed on an HI graph G. So we'll play the game with this for MI. So my opponent now has to choose a monomorphism from some subgraph and hand that to me. But every monomorphism is automatically a homomorphism, and we're playing a graph where I can win the homomorphism game. So I should be able to extend this one to an isomorphism defined on all the vertices. And therefore, I can win this game no matter what choice my opponent makes. So my HI graph is also MI. Okay. In the finite case, this gets a little simpler. The lovely diamond pattern that we saw before gets collapsed a little bit to these 6 classes of graphs, and it relies on this fact or observation that I've made at the bottom here. If you've got a monomorphism from a finite graph back to itself, then it automatically has to be an isomorphism. And you can do this basically by some kind of edge counting argument. Monomorphisms are going to preserve at least the edges that already exist, and they can't create any more when you're dealing with a finite graph. So they're going to automatically have to preserve non-edges, is basically the idea behind this. So therefore, it collapses sort of the symmetry of this diamond, and we're only dealing with 6 classes of graph that we're actually interested in. Okay, so let's look at the bottom one, HI graphs, just to get an idea of how we actually argue with this stuff. So a graph belongs to the class of HI graphs exactly when it's complete, exactly when every pair of vertices is adjacent to each other. So the one direction, which I will draw for you, so suppose we're going to do the contrapositive. So if we've got a graph that is not complete, doesn't matter how complicated it is, it's going to be set up in such a way that I have at least 2 vertices that aren't adjacent to each other. It can be much more complicated than this, of course, but what we do have is 2 non-adjacent vertices, V and W. So my opponent, being a clever opponent, tunes into this fact and defines the following map. We just fix V and we send W back to V. So there are no edges to be preserved amongst V and W, so this is automatically a homomorphism. But now I get handed this map and I have to try and extend it to an isomorphism. Well, this partial map is already not injective. So any extension I'm going to create is not injective either, so I can't possibly produce an isomorphism on the vertices, and I'm in trouble. So my opponent has a winning move at this game, so a graph that is not complete is going to be not HI. So therefore every HI graph is complete. All right. Well, how about the other way? So if we're playing the game on a complete graph, the HI game, why should I always be able to win? So in this case, well, we can be dealing with a complete graph of any size. Let's say 4. Well, if you put yourself in my opponent's shoes for a moment, there's not going to be a whole lot of options available, because every edge is going to have to be preserved, and every pair of vertices already has an edge between them. So you can start out by defining whatever map you like, sort of willy-nilly. You fix this one, send this one over here. But the moment you try and define this map on the second vertex, it's going to have to be adjacent to the image of the first vertex because there's an edge between everything. So this partial map, no matter how we go about defining it, is going to have to be injective. I can't map two vertices to the same place. If I were going to try and define it on the third vertex, I have to avoid this one and this one because it has to be adjacent to the image of everything I've defined so far. So basically, my opponent's choice is limited to an injective map from some subset of the vertices to some other subset. And then it's just a matter of set theory to say, well, then I can just take this partial injective map from subset to subset and extend it to a bijection. And any bijection of these vertices is going to be an isomorphism of my graph because every pair of vertices is adjacent. So every adjacency gets preserved, and there aren't any non-adjacencies to worry about, so I've got an isomorphism on my hands. So this is the kind of graph I want to play this game with, because I always win. All right. So now, let's go to this example, which is a little more subtle. So we're going to prove that a 5-cycle is not HH. Same kind of argument, but all we have to do is exhibit a winning move for my opponent in this game. Some kind of partial homomorphism from a subgraph to another subgraph that I can't possibly extend. I have no hope of doing. And with a little thought, my opponent hands me this one. So this is the map that we can't extend to a homomorphism. All right, let's take a look at why. So I can number these off for convenience. Say 1, 2, 3, 4, and 5. So we've got 3 and 4 interchanged, and 2 mapping to 3. So the only two edges that were relevant here between 3 and 4 and 2 and 3 are still preserved after we apply this map, as one easily checks. So I have to take this map and define it on vertices 1 and 5, some way or other. So let's try to do it for vertex 1, say. Well, the only constraint I have on my hands here is wherever I send vertex 1, it has to be adjacent to the image of vertex 2. I have to preserve that edge. So 1 has to be adjacent to 3, one way or the other. So let's try sending it to 2 first. Okay, well now I have to move to vertex 5. This one has to be adjacent to, I have to send it somewhere adjacent to the image of 1 and 4. So it's got to be adjacent to 2 and 3, and now we have a problem. 2 and 3 don't have a vertex that's adjacent to both, so I'm in trouble. So okay, maybe 2 was just the wrong vertex to choose. I had to send vertex 1 to a neighbor, something adjacent to 3, but 4 is also a viable option. But we're going to hit the same problem now, because if I try and define this in vertex 5, I've got to send it to something adjacent to 4 and to 3. And again, there's no such vertex. So I lose the game one more time. Cool. Therefore, not HH. So you can see sort of the endless fun I may have had as an undergrad sitting in my office drawing dots, lines, arrows, and playing with these things. And again, I think this would be fun to take, say, any 10-year-old nephew of yours or cousin or whatever and explain this to them. And this would probably be a good way to pass the afternoon if you didn't have an electronic device on your hands. Okay. But the game can get more interesting. We can add more rules to the game. Because I hate to lose, I'm going to make things harder for my opponent. So what we're going to do now is restrict the kind of graph, the subgraph that my opponent can choose to be a connected subgraph. So she still has to choose a homomorphism from subgraph to subgraph, but that subgraph has to be a connected one now. So the options are even more limited. And I'm still allowed to extend this in whatever way I want. I can take this partial map and extend it. So now if we've got a graph for which I can win this new game, where every homomorphism from a connected subgraph to another connected subgraph extends to a homomorphism on all the vertices, then our graph is CHH. So this extra C is referring to the fact that my opponent's now restricted to this connected subgraph. And again, we can switch up the kind of morphisms we're playing with, monomorphisms, isomorphisms, and so on, and create 9 new types of graphs, namely CMH, CIH, and so on, with the same kind of hierarchy structure if you attach the C to everything. Okay. Now, if you'll pardon the pun, let's see the difference. So the following graph is CHI, but not HI. So we can immediately rule out the fact that this thing is HI, because that was that toy example we did before, that an HI graph is the same as a complete graph. And I've certainly got non-adjacent vertices in this graph. But it's CHI just because of the way that my theoretical opponent is restricted. So whatever partial map we define, it has to be done on a connected subgraph. So the kind of move that would have made me lose before is no longer possible. So if we've got 2 copies now, well, without loss of generality, let's say that my opponent is starting to define the map on this left-hand subgraph. So, and let's say there's a choice that will have to be made. You either send it to something in the same subgraph or something on the other side. But if you send it to something on the same side, we're now stuck in this subgraph. Any partial map that's defined is going to have to be defined just on vertices that live over here. Which is going to be, and since I've mapped this vertex back to this subgraph, every other vertex I choose is going to have to, the image is going to have to live in this same complete graph, because it's got to be adjacent to the image of this one. So what my opponent will hand me amounts to just some homomorphism from a subgraph of this to another subgraph of this. And we already saw that I can always extend that to an isomorphism in any way, shape, or form. So in this case, I could just swap these vertices and fix this one. And then we've got this empty graph, one we haven't really defined anything on yet, and I can just fix all the vertices. And voila, an isomorphism. So the same kind of argument can be made if the opening move was to send a vertex over here to something over here, because then all the vertices have to be defined on vertices over here, and the images all have to live over here, and I can extend this then to a map that goes, an isomorphism that goes across, and then I can just do any old isomorphism going back. So for this reason, this graph is a CHI graph. Okay. But, so we've seen then that CHI graphs are not necessarily HI, but the other direction will hold, which makes sense because we are restricting the kind of moves that the opponent is allowed to make. So if you're now playing the game where you can only define your morphism on a connected subgraph, and we're playing on a graph where I already know I can win no matter which subgraph my opponent chooses, then certainly I can still win the game under this connected restriction. So every HI graph is going to be CHI and so on. Every MH graph is CMH and all the way down the line. All right, now to the good stuff. What has been done and what is left to be done? So the obvious research problem in this area would be to figure out exactly which graphs satisfy these definitions, produce the complete list of HH graphs, for instance. And for historical reasons, the II graphs in various varieties were considered first. This was, it went under the name of a homogeneous graph, is what it used to be referred to in the literature. And this property being defined first was dealt with first in the late 1970s, early 1980s. Finite II graphs were done, countable II graphs were done, and also the connected variant. So the finite CII graphs were also done in the late 70s. But the countable version of that had to wait a lot longer than that. Just I think because of difficulty issues, not because of anything else. So it wasn't until 2006 with Cameron and Eschatrill that they decided, well, why don't we change up the kind of morphisms we're dealing with on either side of this question? In this game, why do we ask for isomorphisms on both sides? Why can't we ask for other types of maps? So this leads to all these other types that I've introduced, and they managed to deal with the MI, HH, and MH graphs all by themselves in the finite case. Then Lockett came along a few years later and dealt with what we do when we throw the C's in front of everything. So she considered that for the first time and succeeded in classifying these finite CHI, CMI, and CHH graphs. And my job then was to come along. I looked at Lockett's preprint where she had done this, and she noted that there were still some classes of graphs that were left to be classified, so I got to have fun, again, drawing these dots, lines, and arrows and seeing if I could figure out exactly which graphs satisfy one of these definitions. And what I succeeded at doing was dealing with the CMH graphs, at least the finite ones. So the ones that are open, for those of you interested in playing this game for yourselves, anything that has IH in it, CIH or IH is wide open. Finite graphs, countable graphs, with the C or without the C. The countable HH and MH graphs are also open, but we do know that those two families are actually the same. Rusinov and Schweitzer were able to establish at least that much. And then you can throw the C in front of that and also ask the same question. Countable CHH, countable CMH. Those are also wide open for your consideration. Okay. Now we're going to conclude with some family pictures. So we're going to take a look at, and this is not your ordinary family. This family doesn't smile very much, but they do look pretty. So they're going to be we're going to look at the finite connected CHH graphs because, well, it has enough diversity that it'll tell you sort of the interesting phenomena that go on with this type of problem. So they all fall into one of four families. Family number one, known as KN tree-like graphs. So this one is actually the case where n equals 3, so a K3 tree-like graph. Kn is a shorthand the graph theorists use for a complete graph that has n vertices. So I've got n vertices and they're all adjacent to each other. And how I build a Kn tree-like graph is I'm going to take a bunch of copies of the complete graph on n vertices and I start gluing them together on various vertices, whichever ones I like. There's only one thing that I'm forbidden to do. I cannot create a cycle with these complete graphs. So I can't get a bunch of them wrapped around each other. So for instance, I'm forbidden to link this vertex here to this vertex here, because that would create a cycle of 5 triangles all in one big circle, and that is the only forbidden move. Anything else, any other weird gluing that you like is allowed. So here, of course, I've taken a bunch of triangles and just glued them willy-nilly, but you can do this with, say, complete graphs on 4 vertices as well. And after this weird pasting procedure, you end up with a Kn tree-like graph. Okay, family number 2. So these are graphs. They're going to have 2 conditions that we're going to impose on them. The first one is if you look into this graph and you're looking at cycles that literally appear as induced subgraphs. So the only relevant edges between these vertices are the cycle adjacencies. If you're looking at the only cycles of this form that can occur are the 4 cycles with 4 vertices exactly. But the one thing you can't do is you can't have the domino graph show up. So this is not a game of dominoes, it's a game of dots, lines, and arrows. The domino graph, looks like this. So if you take 6 vertices anywhere in this graph, the edges between them can't look like this. They can't look like the domino. But anything else is fair game. So one way of satisfying these conditions would be to have no cycles at all, because then there aren't going to be any cycle subgraphs, so condition 1 is easy to deal with. And the domino already contains 4 cycles, so a graph without cycles will never have the domino. So for instance, you could do this. You could have any connected graph that has no cycles, and these are commonly known by graph theorists as trees, as the picture might suggest, but they don't obviously have to be portrayed as trees. I just happen to have an aesthetic that favors weird, wintry trees without any leaves on them. So trees will satisfy this particular set of conditions. But if we are allowing cycles, you could have something like this that goes on. So certainly, the only cycles we've gotten here are 4 cycles. But the domino graph is not going to show up simply because we have not enough vertices. The domino graph's got 6. This one only has 5, so I can't even find 6 vertices inside to look at to try and find the domino. All right, family 3. So this family consists of graphs that are bipartite, which means that I can split them into 2 groups in some way, like this, such that all the edges are going from one group to the other. There are no edges within either group of vertices. And each part, so each of these 2 groups of vertices I've produced, has to have a common neighbor, which means that there's one vertex on both sides that's adjacent to everything on the other side. So you can think of this maybe as a feud between 2 families in which obviously no one hates members of their own family. Well, I guess maybe you do, but in this ideal instance, you don't hate members of your own family, you only hate the other family. And for some reason, you've got a situation where in both families, there's someone that hates every last person in that other family. Every one of them are just dead to them. So this type of graph, portraying where an edge portrays hatred or dislike, this is the kind of thing that would be a CHH graph.
This wasn't Shakespeare.
No, because then all the vertices would die and there wouldn't be any left. Okay, and family number 4 is also bipartite. So again, we're going to split them into 2 feuding families or just 2 opposite sides, but the only adjacency that we're going to allow all the possible adjacencies that go across. So we've arrayed them in such a way that each one is adjacent to everything on the other side except for the one directly across from them. So in this top one, I picked 3 vertices per side, and the only edge that's missing is the ones that go directly across. Same thing in the second one, it's 4 vertices per side, and I've got all the edges except for the ones that go directly across. So we just pick any number of vertices, same number on both sides, and this is exactly the set of adjacencies that we have set up. So it turns out that these are the complete list of connected examples of graphs that fall into that CHH category. They're all going to look like one of these. There we go. So to proceed from there, if you go back to this hierarchy, it turns out that the CHH graphs are contained in the CMH graphs by the same kind of argument that we made before. So if you're going to build the list of CMH graphs, you can use all the families that were produced by Lockett before, but there's going to be more. And it turns out there are exactly 2 more families. Those are the ones that I came up with to add to Lockett's list to complete the connected examples of the finite CMH graphs. So after all the fancy examples I've showed you, we're going to come to cycles. Turns out, well, these boring old cycles are one of the missing ingredients to completing the list. But these cycles are not particularly boring because they remind me of enemies from Super Mario Brothers. You have your Koopa Troopa shell on the left, and you have your Goomba on the right. And hopefully you don't look at 7 cycles or 8 cycles the same way again. But the second family, well, again, in my weird poetic sense, I've named bridge graphs because I visualized them as the following. We've got 2 islands on the right and on the left, and you want to join those islands by a number of bridges. But the problem is you want to build bridges that all have the same size, and in fact, the size has been specified. It has to have 2 vertices and 3 edges. You're allowed to pick the number of bridges, so you can make them really well-connected islands, but the lengths of the bridges are all the same. So you can choose one with 3 bridges, for instance. The one with 2 bridges is just a 6 cycle. But you can increase the number of bridges, 4 bridges, whatever, any number of bridges. This will complete the family. This is the family of bridge graphs that completes the list of the connected CMH graphs. So hopefully this intrigues you enough that you're willing to look into playing with these and trying to figure out some of the classes we don't yet know. There's, of course, lots and lots of wonderfully written papers where people have played this game over and over again. But so I hope you've enjoyed looking at these pretty pictures of graphs. I hope those of you who have not seen graph theory before now know some of the terms. And those of you who have, hopefully you're willing to take a dive into this problem. And I'm happy to talk to you about this if you are willing to attempt this. So I'm going to show you one more graph as I thank you. One last time.